Good evening to all. So we are going to start in a minute. Okay. So good evening to all. So as I discussed in the last lecture, last time we have finished with the concept of memory management. So we have seen various aspects like main memory, virtual memory, paging, segmentation, various software issues related to memory management, page replacement algorithms, and I also shared some examples in the last session which can be useful for the exams. So on today we are going to start a new chapter which is based on the concept of concurrency. So name of the chapter is concurrency, mutual exclusion and synchronization. So mutual exclusion and synchronization both are very important topics as far as the process are concerned. So whatever we are going to discuss is with respect to the basic process, whether it is synchronization or mutual exclusion. It is the situations which are encountered during the process execution, special circumstances which are happening during the process synchronization, during the process execution, which we have to handle in different ways. So we are going to see all those aspects. So in today's session, we will touch upon the introduction of the concurrency issue, and later on we will see which are the techniques, which are the various techniques, hardware and software related techniques in order to solve the concurrency issue or handle the concurrency issue in a proper way. So the motivation of this problem is based on the concept of multi-programming and multi-processing. So as you know, any operating system, any modern operating system is basically bound to provide the features of multi-programming, that is at a time in your memory more than one process can be part of the main memory, that is multi-programming. So what is multi-programming is many processes in memory. Second aspect is multi-processing, that is multiple processors are available, multiple processors are available, and physical processors are available, and different processes are scheduled on these processors. And the third architecture is distributed processing, in which the process executes, but the architecture is such that multiple nodes or multiple computers are present across the network that are geographically apart from each other. And on those systems, your programs are running. So in all these three architectures, biggest issue is concurrency. Big issue is concurrency. So what is concurrency? What is the meaning of concurrency is that we have to manage the interaction of all the processes together. So all these processes are executing together, and when they execute together, the issue of concurrency arises. So what is the meaning of concurrency? Is that sharing of global resources. So let's say two processes P1 and P2 are sharing common variable, or the shared variable that is common to both. So both of them can have access to that common variable. Suppose this variable is x. So the x variable has access to both processes P1 and P2. Both processes P1 and P2 kind of manipulate these variables. So you should take care that the order in which the process performs read and write operation to the shared variable. Because if P1 performs some operation to X, P2 should also be aware about it. Similarly, if P2 is doing some operation with X, then P1 should also be aware about it. So both these P1 and P2, when they work in the shared environment, they should be aware about each other, and the common variable, consistency of the common variable should be maintained. That is one of the issues in concurrency, global resources sharing. Second issue is optimally managing the allocation of resources. So if P1 is given access to IO channel and it gets suspended before using IO channel, then the performance will suffer. So what I mean is that if P1 is given access of some resource, you have to make sure that the particular resource is used fully before P1 is suspended. Otherwise, what will happen? The P1 process will be suspended and the resource will also be in the intermediate state. So it will not be useful by any other resource. For example, if I'm conducting the lecture from 5:30 and you are joining my meeting, but I'm not taking your lecture and I'm saying that you just wait. I'll start in 5 minutes. I'll start in 10 minutes. So what will happen effectively? There will be no utilization, and maybe you have some other work. Maybe some other faculty wants to take a lecture. So it will not be able. They will not be able to take a lecture because you are not. You are busy in some other session, but effectively that session is suspended. So why this happens? Because I did not synchronize my session properly, and so that due to this, the time utilization is not proper. The third point is difficult to locate programming errors, as a result are not deterministic and reproducible due to overwriting the values. So multiple processes have access to the shared variable. So you don't have a clear idea that which process is doing which kind of manipulation. So if there is any error, if there is any issue, you are not able to track it properly. So that's the third issue. That's difficulty in concurrency. So in general, whenever multiple processes are accessing the shared variable, shared resource, there will be some difficulties. And those difficulties you have to tackle, you have to control in a proper way. And this control of the shared environment, the way in which the shared access is granted, this solution is called synchronization. So that is what we are going to learn. Let's say a simple example. Suppose there is a method echo. So echo method basically first gets a character into the chin variable, and after it gets the variable, it assigns the value of this variable to chout variable. See, the second statement is chout is equal to chin. The first statement is chin is equal to get char. Second statement is chout is equal to chin, and the third line is put char character out. So third line is printing the value to the display. So these are three lines of code. So consider that you have a single processor multi-programming environment which is supporting a single user, and this is the typical scenario in which all of us work. So in this scenario, the user can jump from one application to other, and each application uses the same keyboard for input and the same screen for output. So because the keyboard and screen are shared entities, they are shared between multiple processes. So effectively, when you give input from the keyboard, you cannot determine exactly that where this input is going, to which process the input is actually going. Okay. Similarly, when your output is generated, the output is generated on the screen. So you cannot understand clearly that which process is generating this output. So this kind of issue can happen. So consider a scenario in which each application needs to use this procedure called echo. So it makes sense for it to be a shared procedure that is loaded into a portion of the memory which is global to all the applications. So only a single copy of the echo procedure is used, which saves some space, right? So because this process echo is to be used by multiple processes, we make it shared. We make it a shared process. So let's see a simple execution scenario. Suppose P1 calls echo method, but is interrupted after the first line, right? Let me write the statements here. So what was the process? The first line was uh, input. Second line is assignment, and third line is output, right? C in, then assign, then C out. So P1 calls this echo, but interrupted after the first line. So after this first line is executed for P1, it gets interrupted, it gets suspended. Let's say P2 is activated, it also calls echo and runs till the end, right? So when P2 is executed, so P2 will execute all three statements, 1, 2, and 3. Whereas P1 has executed only first statement. Are you getting? Again, I am repeating. See the same process, there is the same code which you see on this slide, right? So P1, when P1 executes, it will execute first statement and then it will be blocked. P2 will execute all the statements 1, 2, and 3. Now what happens? P1 resumes, but the value is overwritten, right? P1 is resumed, but the value is overwritten. Why? Because P2 has already executed these three lines. So the value of chout variable, is overwritten by process P2. So when P1 prints this second line, it goes to second and third line. Here the output will be Y, not X. Why? Because the value of chout was overwritten by P2. Now why this problem is happening? So it's a very simple scenario. Because your process is shared, its variables are also shared. So it's not like every process will get its own copy. Not like that. These variables chin, chout, all these variables, they have their shared memory. So whichever process manipulates them, their value will change. Their value will overwrite. So the next process, if it reads that value, it will be a changed value. It will be a overwritten value. Now to avoid this solution, to avoid this kind of scenario, what should have happened is P1 should be first allowed to execute all the 3 lines, and then P2 should have been allowed to access and manipulate these 3 lines. But what happened due to the context switch? Due to the context switch, first P1 got the values, then in between it was interrupted. So because P1 was interrupted in between, the values in P2 was overwritten, and then P1 also got the inconsistent values. So precisely the problem here is shared or global variables. The problem is the shared or global variables, or rather the way in which they are executed, that is the problem, that is creating the problem. So you can see is illustrated in a proper way here. So as you can see, process P1 executes the first line, then P2 executes, and then again P1 executes. So there will be an issue. So what we should do, if we enforce a rule that only one process may enter the function at a time, then P1 and P2 may run on separate processors. P1 may enter the echo first. P2 tries to enter, but it is blocked. Then P1 completes the execution, and then P2 resumes and also executes echo. So this kind of rule, if we enforce, we can term it as single access. What is the meaning of single access is that whenever you are working in a shared environment, at a time, only one process should be allowed to manipulate the variable. And when that is completed, you have to get the second process, and then again you can go to the first process. So at that time the synchronization issue is resolved. So what I mean, in other words, let's take a very non-technical example. Suppose we take the example of a lecture scenario. So if you are having lecture of some subject and you are writing notes for that subject. Now let's say after 5 minutes the lecture is not yet over and some other faculty comes and starts teaching. So what will happen? Whatever you are writing, it will be overwritten by the other faculty, and your first lecture, the notes of your first lecture will be no more available to you. Why? Because the notebook, we are assuming it's shared. So what is the better solution? The better solution is that you allow one faculty to take a lecture for 1 hour, and when the lecture is going on, if other faculty wants to take a lecture, he has to wait. He has to wait for the first lecture to be completed, and then he can enter the classroom and take the lecture, because the board, the notebook is shared. So at a time, only one process, only one faculty is allowed to take a lecture. So this kind of scenario is to be handled. It should be created while we work in the shared environment. So from this, a very popular term in operating system and in general in case of shared resources is derived, and this kind of condition is called race condition. Okay, so this condition is called race condition. So what is race condition? To see the definition of race condition, multiple processes or threads read and write the data items. Hence, the final result depends on the order of the execution of the processes. The output depends on who finishes the race last, right? You're getting? So what it says that suppose you are working in a shared environment. Okay, suppose you are in a room and there are 5 people in the room and all of them are making some changes. Okay, all of them are making some changes. Someone is arranging the chair, someone is arranging the table, someone is doing some decoration. Now the first person leaves, second person leaves, third person leaves, fourth person leaves, everything is completed, and the fifth person, let's say the fifth person destroys everything. Fifth person destroys the decoration, fifth person destroys the chair arrangement. Then what will be the final effect? When you next day open the room, what will be the final effect? The final effect will be everything will be destroyed. So person 1 to 4 can claim that we did some good work, but at the end, the result was dependent on the fifth person because he left the room last. So whatever he is doing at the end, that will have the overall effect. And why this situation happened? Because all those persons, they were working in a shared environment. They were working with the same room for the decoration. So again, read the definition. The multiple processes or threads, they read and write the data items, same data items which are shared. Hence, the final result, okay, hence the final result is dependent on the order of the execution of the processes, right? So whichever process manipulates the variable at last, that process will win basically, right? Is that process will win. Okay. So in this way, consider the example, say global variable A is accessed by two processes P1 and P2. Now P1 writes A is equal to 1 and P2 writes A is equal to 2. So what will be the final value of A? The final value of A will be definitely 2. Why? Because P2 wrote the value at the end. So that's why the value of P2 is final. So the loser wins. The P2 who actually came last wins the race. So that's why in the normal race, the winner who comes first wins. In case of this operating system race condition, whoever is the last person, whichever is the last process, that will win. So that's why it's written that the loser will win. So always you have to ensure that whenever there is a race condition, you have to make sure that things are executing properly. And in this chapter, we have to look at the various policies in order to uh, handle this race condition properly and try to maintain consistency as try to maintain the data consistency to the best extent. Now, what is the role of operating system in all these issues? So what kind of design and management issues are raised by existence of the concurrency, that you have to think that, okay, we know what is a problem. Okay, we know what is a problem, but then when we are designing operating system, what is the solution? When we are designing operating system, what is the solution? So that thinking we have to develop from the point of view of OS designing. So see, the OS, it says that the OS must keep track of various processes. The OS must allocate and deallocate resources. The OS must protect the data and resources against the interference. Right. So we can see one by one each point. The first point says that the OS must keep track of various processes, that which processes are executing, which processes are going on, which processes are suspended, which processes are active, that all these tracking must be done by operating system, and the operating system must take care about allocation and deallocation of the resources, and should also protect the data and resources against the interference. Like if one process is getting interrupted, then how to restart it, how to manage that access, that we have to ensure. So you have to manage the concurrency properly. So as I discussed in the previous slide, that when one process is executing and the second process interferes, so how do you control that interference? That is in your hand. In your hand means it is in your hand of the process, in hand of your operating system design. So you have to design some techniques, whether it is hardware or software based, but those techniques you have to design through which you can solve the concurrency issue. Now, what are the scenarios in which the process interact with each other? So effectively, you can define the process interaction scenario in three different categories. The first category is process unaware of each other. So they have a competition. So multiple processes are executing and they are competing for the resources. Meaning of competing for resources, it means that they want some resource for the execution, but they don't know the existence of each other. So it's like, I want to access this particular resource, but I don't know that which other processes are there who also wants to access this resource. So that is the first category. Second category is process indirectly aware of each other. That is also called cooperation by sharing. So they kind of cooperate with each other in the sharing environment. And the third type is processes directly aware about each other. So that is called cooperation by communication. So in cooperation by communication, processes know the existence of each other very well, and they communicate with each other in such a way that they interact and they also cooperate with each other for given tasks. So we will see the detailed examples and scenarios, but these are the general ways in which the processes interact with each other. So let's take the first example, the first scenario. The first scenario is process interaction which are unaware. So what is the meaning of this? Let's take a example of multi-programming. So in case of multi-programming, each process has different goal. Right? Multi-programming, each process has different goal. So operating system needs to be concerned about the competition for the resources. So it means that two processes, they have different goal. P1 is doing something else, P2 is doing something else, but they may want access to the shared resource. They may want access to the shared resource. For example, P1 is a Microsoft Word document, P2 is a PDF document, but both of them may want access to the printer. Okay, both of them may want access to the printer. So that is the example of processes which are unaware of each other, but then they also want to kind of access the same resource. There are many issues in this kind of scenario, and that is one of the uh, most common issues. The first issue is mutual exclusion. The first is mutual exclusion. So meaning of mutual exclusion is that at a time only one process should be given access to the resource, right? At a time only one access should be given access to the resource. So continuing our previous example, suppose if P1 and P2 both need printer, right? As I told you, let's say P1 is a Microsoft Word process and P2 is a printer process. P2 is a PDF process. Both of them wants the access of the printer. So mutual exclusion should be enforced. That implies that only one process should be allowed to use printer at a time. Okay, only one process should be allowed to access the printer at a time. So printer can be called critical resource, and the part of the code where printing is done, the part of the code where printing is done is called the critical section. So the part of the code where the printer is being accessed can be called critical section. So what we mean in mutual exclusion is that at a time, only one process should be allowed to access the code which is there in the critical section, right? So whichever code is there in the critical section, only one of that process should be allowed to access the critical section. Okay, so very important these definitions: mutual exclusion and critical section. So mutual exclusion basically means the scenario in which only one process should be allowed to access a particular resource. For example, only one faculty should be allowed to take a lecture. So that scenario is called mutual exclusion. And critical section is means part of the code which accesses the critical resource. So suppose I have two processes, P1 and P2. Okay, and both of them have print method. Both of them have print method. So this print method is the example of critical section. This print method is the example of critical section, and you have to make sure that at a time only one process should be allowed to enter the critical section. Remember this, at a time only one process should be allowed to enter the critical section. So this phenomena is called the mutual exclusion and critical section and critical resource. So basically why it is called critical? Because if you allow multiple processes to access the critical section at the same time, then there will be inconsistency. consider both these processes, what do you say, P1 and P2, both of them try to access the printer at the same time, and assume that half page is printed by Word document and half page is printed by PDF document. So that's very inconsistent. So what you have to ensure is that when the Word document is being printed, the PDF document should be kept on hold. The PDF document should wait. And only after the Word document finishes the printing, only after the Word document is finished the printing, then and then the PDF document should be allowed to resume the printing, right? So that is the critical resource and critical section. Second very popular issue in case of this category is called deadlock. So what is the meaning of deadlock? Now deadlock occurs due to the enforcement of mutual exclusion. So when you say, see, what is mutual exclusion? Mutual exclusion, you say that only one process is allowed to access the critical section. Only one process is allowed to access the critical section. So the other process is always waiting. So waiting is enforced if you use the critical section, right? If you use the critical section, then waiting is basically introduced. So what is the meaning of deadlock? So consider two processes P1, P2 and two resources R1 and R2. Okay, let me visually represent it for better clarity of the scenario. So I have two processes P1 and P2 and two resources R1 and R2. Okay, now P1 is allocated to R1, right? So P1 is allocated to R1 and P2 is allocated R2. So P2 has R2, right? Now P1 requires R2 to complete. So P1 wants R2, but R2 is with which process? P2, right? So P1 has to wait for R1. Sorry, P1 has to wait for P2, right? See, understand the scenario. P1 is already has R1, but it also wants R2, but R2 is currently with P2. So P1 has to wait for P2. So that is one thing. Similarly, P2 requires R1. So P2 wants R1. Then and then it will complete. But R1 is with P1. So it has to wait for P1. Wait for P1. So it's a very interesting scenario. So what is the interesting thing here? So P1, when P1 says that I want to complete, but I can complete only when I get R2. But R2 is with P2, so I'll wait for P2 to finish. Similarly, P2 says that I have R2, but I want R1, and I will wait for P1 to release R1. So basically, P1 is waiting for P2, and P2 is waiting for P1. But both of them don't know that they are waiting for each other. This is a very typical scenario, and this kind of scenario, basically, it will cause infinite waiting, right? This kind of scenario will basically cause the issue of the infinite waiting, and such kind of infinite waiting is called deadlock. Such infinite waiting is called deadlock. So like, let's say you are waiting for someone and that other person is waiting for you. So you will not move from your place. Like, you assume that classic example, two persons are sitting on the chair in front of each other and they are looking at each other. They are not speaking, but the first person thinks that I will stand up when the other person will stand up, and the other person thinks that I will stand up when the first person stand up. So basically both of them are waiting for each other, but they don't know that they are waiting for each other. And in that process, they have to wait for the infinite time. So this kind of scenario, this kind of infinite waiting is termed as deadlock. And deadlock is very important consideration. And we have a separate chapter on deadlock where we discuss various case studies and some techniques through which we can avoid or prevent the deadlock in a possible way. The third issue is starvation. So again, starvation is also called infinite waiting, but in case of starvation, it's a more general term. So basically, the dictionary meaning of starvation is what? You don't get a food. So for the infinite time, that is called starvation. So it also occurs due to the enforcement of mutual exclusion. So see, wherever there is waiting introduced, the waiting will cause these issues such as deadlock or starvation. So consider three processes P1, P2, and P3, and they need a periodic access to resource R. So resource R is a single instance of resource R is available, and three processes. Let's say this is resource R, single copy. This P1, P2, and P3. These resources, these processes are there, and they want to kind of periodically access these resources. So if P1 is allocated R, P2 and P3 gets delayed. And when P1 exits the critical section, either P2 or P3 will be allowed to enter the critical section. Suppose P3 is granted access, and after P3, if P1 gets access to R again, P2 might suffer from starvation, right? So it's like unfair amount of distribution of the resource to the processes. So P1 is getting resource R, it finishes its job. So when P1 is getting the access, P2 and P3 are waiting. Then P2 is getting the access to resource R, so P3 is waiting. But after P2, again P1 will get access. So P1, P2, P1, P2, P1, P2, it goes like this. So P3 will not get chance to access the resource R. And this kind of scenario, if it happens, it is called starvation. So starvation, deadlock, and uh, starvation, deadlock, and the third issue of mutual exclusion are the classic issues of the process interaction in which they are unaware of each other. So these three issues are very important, and we will see in subsequent sections on how to handle these issues. So the general process structure, the general structure of any process should be as follows. Process P1, so we say while true, some code, then enter the critical section, then there is a critical section, then exit the critical section, and then there is a following code, right? So always you have to maintain this kind of structure where there is a critical section, and before and after the critical section, you can have your code. But the critical section, which is denoted here, should be accessed by only one process. So this should be accessed by only one process at a time. Now then the second category of interaction is the second category of interaction. The second category is called indirect awareness. Second category is indirect awareness. So indirect awareness means multiple processes may have access to shared variables and files and databases. So in those scenarios, they know that they know that there are multiple processes which are accessing these shared resources, but they are not directly aware about it. They are indirectly aware about their existence. So integrity should be maintained. So what is the meaning of integrity is that when multiple processes try to access your shared data, then the data should be consistent. It should not happen that one process writes some data, the other process changes it, and then the original data that you intend to use gets lost. So it should not happen. So that's the second category. Data is held on resources. So for example, memory or other storage. Again, when you have this kind of scenario, you have the similar problems, that is mutual exclusion, deadlock, and starvation. Here the difference is that we only need to make sure that the right operations are mutually exclusive, right? So as you know, there are two operations, read operation and write operation on the shared data. So the write operation should be mutually exclusive, whereas the read operation may not be mutually exclusive, right? So consider your blackboard in a classroom. So we can consider the blackboard like this. So let's say there are multiple students who are reading the blackboard. So can we allow multiple processes? Can we allow multiple students to read the blackboard at the same time? Yes, we can, right? Because there is no loss in that. Because reading is not a critical operation. But let's say if two or three students stand up and they start writing on the blackboard, then it is difficult. Because then the first person writes something, second person may overwrite it, erase it, and ultimately the readers will also not understand that what is going on. So this is the another typical scenario in which you are aware that blackboard is shared and some other students are also reading the blackboard. But then you know that if I am reading, it's fine. But if there is a write operation, the write operation must be mutually exclusive. So that's about the indirect awareness. So one more requirement is there in case of this scenario is data coherence. So let's say consider the code which is given below, and it has to make sure that A is equal to B. Right? It has to make sure that A is equal to B. Because see, A is equal to A plus 1, B is equal to B plus 1, B is equal to 2 into B, A is equal to 2 into A. So at the end of the execution, A and B, both values are same, right? A should be equal to B. But see, if you execute properly, then this happens. But if you execute it in a non-mutual exclusive manner, then it will not maintain this kind of what you say coherence. So consider the example. Consider the first case. So assume that mutual exclusion is done on A and B. Okay, assume that the mutual exclusion is done on A and B. So what will happen if P1 is updating, P2 cannot update A. So if the process executes as given below, then A equal to B will not be maintained. So A is equal to A plus 1, then B is equal to 2 into B, then B is equal to B plus 1, and then A is equal to 2 into A. So basically what is happening? One statement of P1 is executing, then one statement of P2 is executing, then again one statement of P1 is executing, and one statement of P2 is executing. So if this kind of execution happens, then definitely you are not going to have the data coherence. So what will happen? Let's say both A and B, A is equal to 5 and B is equal to 5. So what will happen after this execution? Here A is equal to A plus 1, so A will be equal to 6. B is equal to 2 into B, so B is equal to 10. Then B is equal to B plus 1, so B is equal to 10 plus 1, that is 11. And A is equal to 2 into A, so A will be equal to 10. So at the end of the execution, A will be equal to 10 and B will be equal to 11, which is not quite correct. What you should do is you should have A equal to 10 and B equal to 10. So in this scenario, suppose they execute in sequence, then A is equal to 6, B is equal to 6, and next time when process P2 comes, so B is equal to 12 and A is also equal to 12, right? So you can see that the mutual exclusion has a very key role in managing this kind of data coherence. So what we mean here is, first you should complete process P1. First you should complete the execution of process P1, and then you have to start process P2. So whenever P1 is executing, you cannot allow other process to enter. You cannot allow the other process to enter. And the last category is the process cooperate by communication. The process cooperate by communication. So what is the meaning of this? So in that, when process cooperate by communication, simply they participate in common effort that links all of the processes, right? They will participate in they will participate with each other so that the overall result is consistent. So they are aware about each other and they are kind of cooperating with each other in doing the overall execution. Okay. So the communication provides a way to synchronize or coordinate various activities. So because nothing is shared between the processes in the act of passing messages, mutual exclusion is not a control requirement for this kind of cooperation. But the problem of deadlock and starvation is still present. Right? So here nothing is shared. Every process has its own memory. Every process has its own data, and that data is only manipulated by the same process. So if P1 has some data, it will be only maintained by P1. So there is nothing shared. So every process is executing as per its own code. There is not accessing any shared code in this. But there can be deadlock and starvation. because processes may have to wait for each other in order to do certain tasks. Processes may have to wait for each other. So the issue of deadlock and starvation can still happen because processes may have to wait for each other and they may be waiting for each other for infinite time. That is your deadlock. And also some process is continuously waiting for infinite time, not getting any response, so it's called starvation. So both of these things are possible. So this is just a general idea of the process interactions. So degree of awareness, processes are unaware of each other. Second is process indirectly aware of each other. And so in case of, in first case, everything is shared. In second case, you have to make sure that there is a data coherence. Data coherence is maintained. Data consistency is maintained. And the third part is relatively simple, where processes are aware about each other, so there is no sharing, but there can be issue of deadlock and starvation. Okay. So see, the second and first category are the crucial, and the first category is most crucial because in that processes are unaware of each other. So that should be handled very carefully. So what is the general idea of mutual exclusion, and how we can go about handling handling the mutual exclusion? So only one process at a time is allowed in the critical section for the resource. That's very obvious because we have critical section, and the critical section, only one process should be allowed to execute in the critical section. A process that halts in the non-critical section must do so without interfering with other processes, right? So if some process is halting in the non-critical section, it can do it. Doing that, it should not impact any other processes. No deadlock or starvation is possible. Should not be deadlock or starvation should not be occurring in the system. Process must not be delayed access due to a critical section when there is no other process using it, right? So if, for example, if there are two processes which are using printer, one is the Word process and second is the PDF process, and the printer is free, then any process can access it without waiting because the resource is free. So that is also very critical requirement. Process must not be delayed access to a critical section when there is no other process using it. Then process must not be delayed access. No assumption are made about the relative process speed or the number of processes. So you should not take decision. You should not take decision based on the assumption that you are making about the process speed and number of processes. A process remains inside its critical section for finite time only. This is very important requirement. So process should remain inside the critical section for finite amount of time. It should not be like the process is infinitely waiting inside the critical section. So in that case, what will happen that in order to maintain the mutual exclusion, you are basically creating other problems and you are also wasting the time. Now, how to achieve the mutual exclusion? So in general, if we observe, there are three ways in which we can handle the mutual exclusion. First is leave the responsibility to the processes. So that's a very non-practical approach, because there you are not doing anything yourself, but you are just saying that see, your process, and in your own code you have to maintain the mutual exclusion and concurrency related issue. So that's not possible. It's also not practical approach. Second approach is use the special purpose machine instruction. Use the special purpose machine instruction. So there are some special machine instructions like compare and swap and exchange. So those instructions you can use in order to achieve the mutual exclusion. That will basically reduce the overhead, and it also requires some underlying support from the hardware side. The third approach is support for operating system, support of operating system, which is most popular, and it's also kind of you can say software approach, software based approach, software or programming approach. So through this programming approach, you may plan to achieve the mutual exclusion. So by the way, mutual exclusion, again, I'm repeating this because it's the most important topic, is a scenario in which you make sure that at a time only one process uses your critical section and gets access to the shared resource. So this kind of enforcement is called mutual exclusion. So let's see some of the hardware related support for mutual exclusion. So in the hardware related support of mutual exclusion, we have two methods. The first method is called interrupt disabling. And the second method is called special machine level instruction. So that these are the approaches through which we can maintain the mutual exclusion. So let's discuss the first approach, that is disabling the interrupts. So uniprocessor system only allows interleaving. It means that one process is going on, it will be interrupted, then later on the other process will start. So at a time only one process, you are giving access to that one process. Process runs until it invokes an operating system service or until it is interrupted. So until it is interrupted, the process will run. So disabling interrupt guarantees the mutual exclusion. Right? Disabling interrupt will guarantee the mutual exclusion. Okay, why? Because let's say when P1 is executing, and you want that when P1 executes, P2 wants to execute, but it should be blocked. So it will be possible, because see, when you say interleaving, it means that P1 is executing, then P2 is executing, then P3 is executing, then again P1 is executing. This kind of switching, see, this is interleaving, means basically switching. So switching is done through interrupts. So switching is done through interrupts. So you can refer the process chapter for more details. Like we have seen how process switch occurs, right? So when process switch occurs, the interrupt will be generated, and that interrupt will basically switch the process. But what you are doing, you are disabling the interrupt. So you are disabling the interrupt mechanism. So due to that, what will happen is when a process is going on, no one can stop the process until it gets fully executed. Okay. No one can stop the process until it gets fully executed. Why? Because there is no way for it to get interrupted, because interrupts are disabled. So this solution, that's why this third pointer in the first para is written. It says that disabling the interrupts will guarantee the mutual exclusion. Disabling the interrupts will guarantee the mutual exclusion. So that is the first part of this hardware-based solution. So what kind of code we can visualize is that when the process starts, first we will disable the interrupts before the critical section starts. Okay, before the critical section starts, we will disable the interrupts, and once the critical section is over, then we will enable the interrupt, and then the remainder of the process can execute. This is in general overview. But doing so is not a very practical solution, because see the issues, execution efficiency is degraded as the interleaving gets limited, because you are now and then disabling the interrupt, so it will impact the overall performance of the system, and you will get less switching, and it will affect the overall performance of the system. Also, it will not work for the multiprocessor architecture, because you are not going to go to each processor and kind of disable the interrupts. So in general, it doesn't seem a practical approach for the disabling the interrupts. So we have a second way of solving this issue, that's called special machine level instructions. So in special machine level instructions, we have two instructions, which is called compare and swap, is also called compare and exchange, and second is exchange. So we have two instructions which work in a special way to kind of solve this issue. So what is compare and swap instruction? So compare and swap is one method. This instruction, basically it will take three arguments, so old value and new value. So it will first check the old value. If old value is equal to test value, then it will swap it and return the old value. So basically it will compare two values, and if they are same, then they will be exchanged, swapped, and it will be returned. Let's see one example. So yeah. So this version of the instruction checks the memory location against a test value. So there is a memory location which is called world, and world is checked against the test value. If memory location's current value is equal to test value, then it is replaced with the new value. Otherwise, it is left unchanged. And the old memory value is always returned. Thus, the memory location has been updated if the return value is the same as the test value. And we will see how it works in a moment. But this is an atomic instruction. So this you have to make sure. Now, what is the meaning of atomic instruction? So atomic instruction is very important term. It means that this instruction is either executed fully or it's not executed at all. Okay, this instruction compare and swap, either it executes fully or it does not execute at all. So this kind of instruction is atomic instruction. There is no chance that it will get hanged in some intermediate state. This compare and swap instruction, there is no chance that it will remain in some uh, middle state. Either it will be executed fully or it will not execute at all. So let's see the program. So the program is, see, we have n number of processes. Suppose this n is equal to 5. So we have 5 processes. There is some variable bolt, and we have a process P. So when the process starts, every process, right? Every process, when every process starts, it will execute this compare and swap bolt 0, 1. And if compare and swap bolt 0, 1 is equal to 1, then do nothing. Like it's an infinite, right? See, this kind of statement, while followed by semicolon, in programming is called infinite waiting. It means when this condition is true, it will remain at this line only. It will not go ahead. So infinite waiting. Okay. If the condition is false, then it will go down. So then the critical section is executed. And at the end of the section, bolt is equal to 0. Okay. At the end of critical section, bolt is set to 0. And then the remainder of the code can execute. So see the overall idea. So bolt is equal to 0 initially bolt is equal to 0, then different processes are executing together, P1, P2, P3 up to Pn, right? All processes are executing together. So how it will execute? So see, bolt is initialized to 0. First call, so let's say P1, it will be compare and swap 0, 0, 1. Why? Because bolt is 0. So 0, 0, 1. Okay. Now what it will return? So see, this is 0, 0 and 1. So what is old val equal to world? So old val is equal to 0. So if now 0 is equal to test val, what is test val? Test val is also 0. Then world is equal to new val. So world will be equal to 1 now. Okay. World will be equal to 1 now, and it will return old val. That will return 0. Okay. It will return 0. So in this code, it will return 0. So 0 is not equal to 1. So this process will start, right? So world and test val are same. So world will get updated and return value is 0. So P1 can enter the critical section, right? P1 can enter the critical section. Okay. But you see that when P1 is entering the critical section, the bolt is getting updated, right? Bolt is getting updated because of this instruction world. This instruction, the bolt is getting updated. So now the current value of bolt is equal to 1. Current value of bolt is 1. Now let's say in this same scenario, P2 calls this compare and swap instruction. In the same example, when P1 is still executing, P2 is calling compare and swap, but its bolt will be 1. So this will be 1, 0, 1, right? So it will call with 1, 0, 1. And the return value of this, if you execute this code, it will not change the value of bolt, but it will return 1. So if it returns 1, then this condition will be true, right? So it will be infinite waiting. So P2 will wait here. Okay, P2 will not move ahead, it will wait here. Till what? till the value of bolt is 0. Okay, till the value of bolt is 0. So who will set the value of bolt to 0? The process P1 will set the value of bolt to 0 when it finishes the execution, right? So when P1 finishes the execution, it will set bolt to 0, and then the while condition will become false, and P2 will be able to enter the critical section. Okay. So this is very interesting application of the compare and swap instruction. Again, it's a hardware level instruction. So either this instruction is executed fully or it is not executed at all. So we have to use this instruction in order to maintain the mutual exclusion, right? So mutual exclusion is maintained like this. So we have one more instruction, that is exchange instruction. But this exchange instruction we will take it in the next session. So before that, if you have any queries for today's session, you can interact. Otherwise, we can close the session. The most important takeaway from today's session is the concept of mutual exclusion is the situation, the scenario in which you allow only one process to enter the critical section. And to do this, we are looking at different solutions, hardware-based, software-based. Those solutions we will discuss in detail. We have just started with the concept of hardware-based instructions. Okay, I guess no more queries, so we can end the session here.